Right now, there's an invisible battle being fought to keep your lights on. Our power grid, this incredible feat of engineering, is constantly under attack. Today, we're going to pull back the curtain on these threats, what we call grid faults, and understand how they can instantly threaten the power we all rely on.
So what is it that we're actually defending against? Well, the real danger comes from sudden, totally unpredictable events that can throw the entire system off balance. And these events have a name: faults.
So what exactly is a fault? Well, at its core, it's an electrical failure. The one you've probably heard of is a short circuit, and that's simply when electricity finds a new, unintended path to travel down. Think of it like a sudden, massive leak in a high-pressure water pipe. It's a critical problem, and it has to be dealt with fast.
But here's the thing, not all faults are the same, not by a long shot. So let's start with the one that engineers and grid operators have to deal with most often.
And when you look at the numbers, well, it's pretty eye-opening. A whopping 80% of all problems on the grid, that's 8 out of every 10, are something called phase-to-earth faults. So by a huge margin, this is the most common headache the system has to face.
So, that massive 80% figure we just saw, this is it. It's what's known as a single line-to-ground fault. It's actually quite a simple idea. You have a power line with 3 wires, or conductors, and one of them accidentally touches the ground. That's it. A simple concept, but it's the #1 cause of disruptions on the entire power grid.
So you might be wondering, why are they so incredibly common? Well, the reasons are often things you see every day. We're talking about lightning strikes, tree branches falling onto lines, strong winds, or even a squirrel in the wrong place at the wrong time. It's this constant, relentless barrage from the natural world that the grid has to stand up to, day in and day out.
All right, so we've covered the most frequent fault, but now let's turn our attention to something much, much rarer, and yet something that keeps power system engineers up at night.
Okay, so broadly speaking, you can split all faults into 2 main camps. On one side, you have unsymmetrical faults. That's the single-phase one we've been talking about. Think of it as being unbalanced. It only affects one part of the system. But on the other side, you have symmetrical faults, and these are different. They hit all 3 phases of the power line equally and all at the same time.
And that's exactly what a symmetrical fault is. It's just another name for a 3-phase fault. This is the scenario where not just one, but all 3 of those conductors get short-circuited together. We're not talking about a single part failing anymore. The entire power line has been compromised.
And this really gets to the heart of why these faults are taken so seriously. Because they're so rare, you might think they're not a big deal, but they produce the biggest, most powerful surge of electrical current imaginable. You've got all 3 phases dumping energy into the fault at once, and the result is, well, it's immense. This is the absolute worst-case scenario, and it's what every single safety system on the grid is ultimately designed to handle.
Okay, so let's put these 2 ideas together, because this is the fundamental challenge for anyone trying to protect the power grid. It's a constant trade-off between what's common and what's truly dangerous.
This table really lays it all out, doesn't it? On one hand, you have the single-phase fault. It happens all the time, about 80% of the time, but it's less severe. On the other hand, you have the 3-phase fault. It's incredibly rare, only about 5% of all faults, but it is potentially the most destructive. So you see the dilemma? The grid has to constantly manage these frequent, smaller problems while always being ready for that one rare event that could be catastrophic.
So why does any of this analysis actually matter? I mean, what are the real-world consequences if one of these faults happens? Well, if a fault isn't found and cleared in literally milliseconds, the dominoes start to fall. And fast. First, you can get physical damage to expensive equipment. Then you can see huge voltage drops across the network, which is bad for everyone connected. Generators can be knocked out of sync with the grid. And in the worst cases, there's a real risk of fire, danger to life, and that dreaded cascading failure that leads to widespread blackouts.
And that's why this analysis is so absolutely critical. It's not just theory. It's what allows engineers to fine-tune all the protective devices across the grid. You can think of these devices as the grid's immune system. Their job is to spot a problem the very instant it happens, and then surgically isolate that one faulty part before the infection can spread and take down the entire system.
And this brings us to a final and really important thought. Our power grid is changing. It's becoming more complex with new types of energy and new ways we're using electricity. So the big question is, how do we make sure our defenses keep up? The challenge isn't just about protecting the grid from the faults we know about today, it's about preparing it for the unknown threats of tomorrow.